Okay, I'm in the room. I hope I've got things a little bit better set up. I'm going to wait until some other people join, and I need to switch a memory stick over so that I can show you some images. In the meantime, I'm going to visit the boys' room. Okay. Hi Artifact, hi Corky. Right, I am going to show you a whole bunch of images that hopefully you'll be very clear about how this feature was produced. And I first want to, whilst we're waiting for people to come in the room, is to go through a whole bunch of questions that people had last night that I think I can answer quite quickly. Just go through those whilst people are potentially coming into the room. So let me have a look at that. So the first question that I hadn't answered last night that I wish to answer tonight is the answer that we're going to deal with first, and that is, could you explain how the sample was made? So that was Hidnik who asked that. Mescal, as in M3SCA1, he asked, cold neutrino, is it harmful? I would answer yes and no. It depends on the quanta. It is very clear that this is absolutely ubiquitous throughout the universe. We have evolved with it. It is absolutely everywhere in our environment in unimaginable quantities. However, the exotic vacuum object appears to be able to condense these things into solitons. And just like you're quite happy to swim in the sea, that's fine. But when you have a tidal wave coming towards you, a tsunami, it can do you damage. And what the Russians are suggesting is that these cold neutrinos can be condensed into these solitons that Alexander Shishkin calls magnetotoro-electric radiation, MTER. And the neutral form of this can be carrying ions, and when it breaks up, for instance, in a human body, the ions can be shot out at such an energy as the neutral EVO is disheveled, that the ions can destroy red blood cells and damage DNA in white blood cells. I have also argued that the ability of these things to cause inverse beta decays, as is explained and discovered by Alexander Parkhomov in his book Space, Earth, Human. You have two principal beta isotopes in your body in massive abundance. One is 14 carbon. This is 1 part per trillion in your body, but when you consider every mole is not one with 12 zeros, it's one with 23 zeros. There's a lot of carbon-14 atoms in your body, and this is the basis of carbon-14 dating, you know, when you do carbon dating of things. And the reason you do carbon dating is that the carbon-14 is formed in the upper atmosphere. You have, I think it's an NP or PN reaction, and the nitrogen-14 goes to carbon-14, and this is then breathed in or by plants, and we eat the plants, or the animals eat the plants, and then we eat plants, or the fish eat the algae or the protozoa or whatever it is, the krill eat the whatever, and you end up with this in the food chain. And so when you are alive, you absorb carbon-14 into your entire body, and when you die, you then don't absorb any more carbon-14, and so that starts to decay, and it's got a number of thousand of years half-life. So this is how that works, that carbon dating. So you have a lot of carbon-14 in your body, and you also have potassium-40 as well. It's 0.012 or something, much less than 0.1% of normal potassium-40. And that mostly decays. It can do a positron electron capture and a beta decay, but it mostly decays naturally by a beta decay, which is 1.331 megaelectron volts. However, with the condensed soliton of cold neutrinos, this can stimulate the beta decay, and that fires out these extremely high energy beta particles, which will cause cancer. The direct one is the fact that the sugar molecules that are in your DNA strands, they contain carbon. So your DNA is bound together in part by a molecule that contains carbon, and 1 part per trillion of those carbon atoms will be carbon-14. And so exposure to this can cause, at a certain quanta, can cause cancer, essentially. And Ken Shoulders died of cancer, and the person that made as far as I understand it, the person that made the supernova reactor, he died of cancer, and Norris Peary died very suddenly as well. So, and also Yuji Bajatov. So this is real risk when you are making these large quanta. But I do believe that life actually leverages this in cells to get nuclear level energy. And it does that in a way which is harmless to biology. It works within the limit of a subtle approach to manipulating matter within biology. So you've heard of biological transmutations. So, okay, so yes, it's harmful. And the Russians have done some studies. They've done some studies with mice. So they've taken these mice that you have in labs. When I worked at SmithKline Beecham in Worthing, they had an animal testing lab there. Not something that I was involved with, but it was there. And they had rabbits and so on. But you get these mice that are predisposed to getting cancer, or just they're normal mice, or rats. And what they did in their testing, I think it was in between 2009 and 2019, they had a water cavitator using like a hydrosonic pump. These are possibly the most dangerous excess energy technology you can have, and I will discuss the kind of levels of intensity of producing EVOs at another point, but really cavitation is the way to really kill yourself quickly, mostly because you can create very large nuclei that decay, and they produces radioactive nuclei, but also it produces a lot of strange radiation. So Shishkin has this cavitator, and exposure to that of about 1 hour at 1 meter will kill a human. So there is a real worry for people that work near pumps that might be damaged and things like that, which there's no understanding in the workplace of the risks of this, and also spinning bodies generally, because they output a certain quanta of this type of strange radiation. Anyway, the test that they did is they exposed some mice to the generator before exposing them to gamma rays that would cause cancer, and some of them they exposed the gamma rays to the mice prior to exposing it to the strange radiation. And in the case of the people, the mice that were exposed to the gamma rays beforehand, the exposure to the strange radiation accelerated the cancer. And those that were exposed to the strange radiation beforehand, it's, as far as I understand it, and you need to go and check the papers, but it stimulated the production of white blood cells, and so when the mice were exposed subsequently to gamma that would ordinarily cause cancer, they actually, as far as I understand it, and you need to go and check this, they had a lower incidence of cancer. And this is why it basically kind of accelerates life. And another thing that they showed in the Sochi conference, where they were doing corona discharges into water, and this will produce strange radiation, and I will explain that gets bound into the water, specifically oxygen, and that's a very important part of all these technologies that involve water. And there's a whole other subject that I will get into in short order, actually. This water produced seedlings that grew faster and were more resistant to pathogens. And actually, Shishkin uses the water from his cavitator with plants as well. And you can imagine that if a lot of nascent monoatomic new fresh nuclei were synthesized, the water would be very nutrient rich for organic life. And I've said this since 2017, that the water, tap water going into the echo reactor would play two roles. It would play one role in preventing the buildup in the metal of high quantities of strange radiation, and it also provides a barrier. And so I've been working with Henk, for instance, on shielding along these lines. But the water would then absorb this, and we know from the 2011-12 outside exposure with magnets that water can accumulate this quanta. So if you've got constant flow through, you can heat the water. It will take on board some of the strange radiation quanta, but not building up to a dangerous level, potentially, or hopefully not. But it's preventing the metal from getting overloaded with it. And then the water itself is then very good, in my opinion. The wastewater from, say, the echo reactor would be good for agriculture, for instance. So it would be more than just the water you put into the reactor. So you could get like multiple whammies out of this. It would be great for like hydroponics if we were on a different planet, and there was less nutrients there. And this is how I argue that the cavitator, the vibration plates of Amasa would be producing water that could be beneficial to organic life. And it's akin to water flowing down a stream. And as it's going down the stream, it's causing cavitation on the rocks and on the stream bed and just within the water. This, I believe, creates water that is more vital than even rainwater. Of course, rainwater might be charged electrostatically. There might have been lightning, so there might be all kinds of things going in there. But the water going down the stream, it's not all water is the same. And I think when people wake up to this, water, and I believe a large proportion of why water is not always the same, is because of its ability to absorb the history of its experience. And one of the ways that it can absorb that history of experience is if it's exposed to lightning, if it's exposed to cavitation, it will be materially different. It'll taste the same, pretty much, probably. And I think this is also the case when you have water that's, for instance, coming out of a spring. That water rained, but as it's going through the mountain and so on, it's percolating through, and then it may have had some. I think Malvern water. It's something like 100,000 years before you get the water out that rained. It's a very, very long time. It's in many thousands of years, I think. And if you've ever been down some of those sort of central England or northern England cave systems, and I've had the pleasure of going potholing in Wales and in various places in England, you will understand that the water shows its history inside the cave systems, and it's absolutely certain that the rippling that you see on the walls and stuff, that is the water doing that, but in doing that it will produce cavitation, so that the water is not only mineral rich. I think there's something more special going on in that water than just the mineral content, and it might be good from a point of view of quanta of strange radiation or quanta of condensed neutrinos or whatever that are beneficial and just not even on the radar of modern science. So anyway, okay, so we've got 14 people in the room. So Ron Muckler says, I'm sure I'm affected by full moons. I really wonder about neutrino flux. Okay, Ron Muckle. In 2013, so I think Kevran and also people, I think going back to 1598 was the first sort of biological transmutation study, and I think that was a seed study. I need to confirm that, but certainly in the mid-50s they were doing seed studies, and what they found is that the amount of calcium or whatever it was, or potassium, there was a change in elemental nutrients in dry weight, from the dry weight of the seeds to the dry weight of the germinated seedlings, even if you had deionized water. Now, as I'm saying, the deionized water may actually contain packaged nuclei inside EVOs, which are bound to things that are already in the water. So this is a situation where the biology might be able to extract something that's in the water that you can't analyze to find anyway. But let's assume it is just straight H2O. There appears to be some transmutation going on. And what was found is that different people had different experiences where they didn't see any transmutation. So, some people just thought it was bunkum. Now, an Indian study in 2013, if you go to our Facebook site and search for, that's the MFMP's, Martin Fleischmann Memorial Project's Facebook page, and you search for sort of moon phases or seedlings or something like that, you'll find this. But it's a paper that was done in 2013 in India. And what they did is, rather than just randomly start an experiment at some point in the year, they, over the course of the year, a few days apart, they started the germination process of seeds. And what they found is, depending on the phases of the moon and the moon within the year cycle, they found that you got this increased levels of new elements in the or potassium or whatever it was in the potassium or calcium in the dry weight of the germinated seeds, as opposed to the dry weight of the seeds to start with. And this implied that the moon was playing a role. Of course, if they looked at Parkhomov's work, they would realize that, and also the work of Xu and Zhu, they would realize that the moon is able to manipulate this flux of cold neutrinos. And when I was living in India, this was very, very interesting to me, because they would always have these auspicious days for doing things. And my father was a farmer, and there is a right time to plant seeds. There is a right time to do certain agricultural processes, and it's not always the same day. And so when you take on board the fact that the neutrino flux is affected, the cold neutrino flux is affected by the position of the moon, I would suggest there is a major effect. And you also get these comedies that, you know, my girlfriend or I'm affected by the phases of the moon. I'm also affected by electrostatic charge quite seriously, and I'll talk about that on my blog in the future. But in the terms of the moon, there is anecdotal evidence, at least, that the moon affects people's moods and so forth. And is it something to do with this cold neutrino flux, which appears to be a factor in all biological processes? Okay, so yes, Ron Muckle, there is an effect by full moons. Stuart Nash, I think Tesla was catching cold neutrinos, but he called them radiant energy. He had a solar panel and they still worked at night. Yes, I believe he would have been doing. I also think that a number of people that have captured this so-called energy from the environment would have been capturing these cold neutrino flux. One example I think is Henry Murray, and a couple of factors. Like Tesla went into the desert and so did Murray, and that's because there's electrostatic charge, but it doesn't get, you get static build-up on dry days rather than wet days, so it doesn't dissipate. And if you have static electricity, you have a potential to interact with this cold neutrino flux. So I believe that in dry environments and environments where static cannot dissipate and you can get a build-up of charge, then you have a higher chance of forming aggregates of this material. And I think this is important for John Hutchison, where he would always put his samples on, say, a plastic crate or a piece of wood or paper. And this is to prevent discharge of the material into the ground or whatever. And in the case of Murray, he would be capturing these things, conducting them down a wire, and then they would stimulate in his radioactive isotope maybe beta decays. The beta decays would then cause secondary electron emission processes, and those would then go to sort of Townsend avalanches, and and these would then feed into the EVOs that are coming into the system, and you would get a lot of energy. And note also that he is in his famous demonstration, he is lighting light bulbs, which at the time would be tungsten filament light bulbs, and we've already demonstrated that tungsten is highly affected by exotic vacuum objects. And this, I shared a video a long time ago, which was actually came out of it's in Tom Bearden's book. They went and saw this observed in 1992, but they tried to commercialize it again, I think, in the late 2000s. But they had an 8 micron wire, and they were able to use a Tesla coil and a spark gap and then feed whatever it was down these 8 micron wires, and then light, I think it was something like 25 kilowatts of tungsten light bulbs. But it is because of the way it interacts with it, which is not what you would expect. So it's giving the equivalent light output, but it's doing it in a different way. And you will have seen this with the Amasa gas on tungsten. The tungsten is nowhere near its melting or boiling point or whatever, but you're getting a very incandescent light from that. So yes, I think he probably was capturing cold neutrinos. And in fact, with his ray gun, he has a dry steam jet, so you've got your oxygen and your HOH in there, and he effectively creates a vacuum in that, so it's an open-ended vacuum tube, and he has either a tungsten wire feeding in or a mercury droplet, which would produce a Taylor cone, and he then produces, I think it was described it in 1932, electric particles of matter, basically an EVO, and these would then go through the water, and this would produce his beam, and it's very similar, if you think about it, to what kind of going on in a cavitation bubble. You've got charge separation, and then it's coming together and it's going through water and so forth. So it's all the same thing. Okay, so Felix Ardate said, why do you feel it's important to show this in great detail? I feel it's important, Felix, because people don't look at things. They assume that they already know how it happens, and it's actually not important to most people's lives. Most people that have ever lived never needed to know about exotic vacuum objects. However, if we, in my opinion, are going to solve the energy problem and safely, but also to be able to travel efficiently to different solar systems, and also to be able to terraform those solar systems so that they are compatible even if they weren't before. But let's say you've got a habitable planet in the habitable zone of a sun, but it hasn't really got enough carbon, for instance, or enough nitrogen. You can go there and you can use this technology to basically produce the elements you need. So I think it's extremely important to look at these things and understand what's going on. And I think really Shoulders and Takaaki Matsumoto were really the pioneers of that. We're not really seeing so much Evo tracks. I think what you're seeing on the screen here might be Evo tracks. So if I go and draw here, this one here might be, is it going to work for me? Let me try. This one here might be a Evo trail. There, maybe, don't know. Was this cathode in a liquid, Gordon Doherty? If so, what was going on with the interactions between the cathode and the liquid? No, it wasn't, and in a little while you'll find out exactly what how this was made. Gordon Doherty would likely inform the path of any electrical discharge would follow. Yes, if plasmoids cause these, then we would expect transmuted elements. Yes. I probably not tonight, but I want to go over a presentation that was produced in 1996 by Takaaki Matsumoto, and he showed these hexagon structures with new synthesized elements that weren't in the reactor beforehand, and this was effectively discharges. So in my view, he is creating a coherent matter that was formerly called plasmoids, and then called electron validum, and then called charge cluster, high density charge clusters, and then finally exotic vacuum objects. But I think it's coherent matter. In that case, it's the pinching at the anode that's causing it. But as you'll see today, the cathode that we've been looking at yesterday, this is actually at the cathode. Now, exotic vacuum objects can be born, and often are, at the cathode. And I will look at other research and explain, how these can occur, and why certain things like dendritic structures, and also certain types of carbonyl nickel formations are very good at birthing these structures that then can go on and do work in LENR systems even after the entire piece of nickel is just a molten blob. It's actually the spikiness on the surface that allows for the space charge to build up to a point that effectively it causes a coherent matter formation that rips off a section of that spike, and then it continues to get charged by field emission, and then you get a Coulombic explosion, and the Coulombic explosion leads to a large amount of strange radiation that then goes and accumulates in the matter, in the metal, because it can, and as these aggregate together, you then get something that can do LENR. And so you can imagine that this would be what happened in the Parkhomov 225-day reactor. And if you go and look at my ICCF 21 presentation of Parkhomov's 225-day reactor on the Martin Fleischmann website, you will see me when I'm asked, about, how this is going on. I'm saying that, whatever's going on, the thing is made at a lower temperature, and then it persists and continues to work in whatever temperature you make the reactor operating at. Okay. And so C. Holmes said that he has various analytical techniques, waveform dispersive spectroscopy, X-ray fluorescent, and so on, and it would be very useful. So there we go. Okay, so I'm going to start pulling up some images. I'll just see what you've said here. Maybe I can see what you've said here. Let me eject this thing over here. Okay. Maybe I can see these images, I don't know. Okay. And I need to switch here and switch here. Okay. Make that so I can read it. Okay. So what are you saying? Felix, about HHO, yes they can, but water does accumulate these, and it really does depend on the nature. I'm in the middle of writing a paper with respect to Marsa gas, and I think I'm gonna just change the view here. You've got something different to look at. I'm doing a paper with respect to Marsa gas, and this will be very relevant to that question. So I don't want to get ahead of myself on that. But I think really, certainly in the case of a Marsa gas, it is LENR in a can, low energy nuclear reactions in a can. And I would suggest that brown gas, and we will know this when we can travel and we can test that brown gas generator that we have in the US, we will know whether that can do the same thing. But essentially, very quickly, the charge separation, the cavitation, the disassembly of the water molecule in the cavitation formation and collapse will lead to quanta of this material being produced, and it will aggregate, and it becomes part of what causes the heavy gas. And when you burn that heavy gas, it then it releases these structures, and the structures then aggregate, and you effectively create exotic vacuum objects on the fly, and the exotic vacuum objects can then transmute matter and do all the funky stuff like turn various melting point metals to liquid so that you can fuse them together. Like you can get, I don't know, iron and fuse it to glass without the glass cracking. And weird stuff, but it's because it's melting it in a non-thermal way. It does get hot in that case, but you are able to create this change, this phase change, which is not normal melting. Okay. Yeah, we can mess up the carbon dating, that's true. Leclerc, yes, Gordon Doherty, Leclerc, yeah. Yeah, he nearly died. He had full-on radiation poisoning, and he puts it down largely to the synthesis of very heavy elements that then fission, and they have their normal radioactive decay like cesium-137, strontium-90, and things like that. However, he observed in tracks on his apparatus and on his material, and further out in his lab, the same kind of strange radiation track that we've observed in many systems now. And so it isn't the normal sort of radiation that necessarily was all of the story of why he had his poisoning. And so, yeah, I mean, if you really want to create nasty levels of this radiation, then the cavitation is the way to go. And the more intense the cavitation, the worse. That's why I like the Marsa gas, because it's kind of subtle. Okay. Greetings from us. Hey, how you doing there? Okay. Yeah, exclusion zone is important, but I will come to explain why I don't think that's necessarily all of the story going on. It is an important factor, mescal, but it's not, in my view, the most important factor as to what creates the actual material that you want. Okay. Yeah, you can store energy between para and ortho hydrogen, but again, it's not the important thing here, in my view. That's interesting. Putting water through pipes containing rocks. Well, the rocks will cause cavitation. There you go. Okay. Such water appears to be more energetic. Can't remember the details. Yeah. I would imagine so. Yeah. Okay, so that's... So I'm just reading your comments here. Okay. Who built the moon? Okay. Okay. All right. So I'm going to start talking about this cathode and how it formed, and maybe I'll come back to your questions. There's a lot of questions there. This is why I'm comfortable with just 23 viewers rather than several thousand. I'd never be able to cope with that many. I don't think. Okay, so let me see if I can pull up a window of these images, and we can then discuss them. So, how do I zoom into that? Okay. Right, I'm going to try and get a different view here. Okay, this should serve our purpose. Okay. Let me know when you get bored. Right. Talk amongst yourselves. Aha. Okay, I think we've got something that's useful here. Okay. And I'll just pull up my mugshot, if that'll work. I didn't ask if anyone can hear me, but I assume you can. Otherwise, it's going to be comical watching this play back. There we go. Okay. Not that you really need to see me, my ugly mug. Okay, so can everyone see that? Okay, so I shared this image as the title of the Valley Forge presentation that we're doing here, and there is several images that you can see on this frame which are to do with the layout that caused this. So first up, what you're seeing in the this area here, if I actually mark it on the slide, this area here, helps if I actually do something useful like this. This unit here is this one. So this is an electrode. I don't believe it's magnetic. I will be able to test that. And that was the anode. Hold on, I'm just getting it extremely strong. No, it's not magnetic. So here, it's not magnetic at all. And so that was the anode that you can see in that frame there. And so you can see the scale of it. I've got some calipers. I can tell you the diameter of it. It is just around about 20 millimeters there. You can see that 20 millimeters, and it has something like an M8 or an M6 screw thread in the back there, and it has a little chamfer on the edge. I think you can see that there, and that is where you are seeing the formation of the so-called balls of fire, according to that Fusion Technology or Fusion Journal 2001 paper, Japanese paper. So that is that, and what we are going to discuss is so effectively we got these little balls of fire going around that chamfer area here, and then that's the anode, and down here is part of the cathode, and this also has balls of fire. So the interesting thing here is effectively when you see these balls of fire in the sapphire experiments, it's kind of like one part of the story, but that's because you're condensing the material in kind of like a pinch from a very large cathode rather. The field emission of the electrons are coming down to the spherical anode, which is relatively much smaller, and you're getting this wonderful control there. However, you can actually produce these balls of fire on the cathode, and you can see it very clearly here in this frame. And it's not surprising because this is actually where the electrons are coming from. So, let's go and look at these frames. So we've got 3 frames on here. I don't know whether you can see that. Maybe if I come up here, yeah, maybe. This one here, what we have on this section here is a piece of angle iron and another one here. And on the top, there are these brass plates here and here. And on the bottom here, these tubes are basic copper plumbing tubes. So I'm going to see if I can find the full frame image of that. I've just rotated it here. So the reason Henk did this was the opening to his reactor was too small. And sorry, I'm just going to. Corky's just said lightning starts at the ground. No, lightning starts at either the ground to the cloud to the ground, or the cloud to the cloud, depending on the potential difference. Anyway, that's just a point there. So here you've got brass on the top. These are the angle iron, and this is the copper tubing over here. And how he arranged this, he's sent this wonderful drawing through here. Copper pipe. The reactor was effectively like a pill, but a pill laid horizontally, and in the cylindrical section you had these copper pipes, and the copper pipes were, as you see the copper pipes here from the top view, this aspect, this left to right, is the same as the left to right here, but from side view. And here are your your angle iron, and the structure was arranged on top. And this is the anode, and so actually this cathode ran with a number of anodes, of which the one that I've shown you is here, but also he ran it with a spherical anode, in fact one other anode as well. So this 15mm ball here was also run, as far as I understand it, with that arrangement. And you can see you've got the anode terminal here and the feed through. So there is about 10 centimeters between these two, and the tank had a diameter across from left to right of 40 centimeters. So you can get an idea of how large that is. That particular ball is made of iron, I think. He had this one, I think he ran it in there at one point as well, which is tungsten. And when we look at the elements in here, we're going to have to discount all of the elements that are in these various anodes, because if you imagine that if there's ions made, the ions will want to travel towards the cathode because they're positive. So you would expect them to be dumped there. Size does matter. So for instance, when he used larger balls, they were less successful. In fact, actually 15mm is a good size for the tank that he was operating on at that time. So and of course that depends on how much power you can feed in and so forth. So this is the main support structure, but on top of that, if I can find it, is it in here? I need to go view. If I can find it. Is it in here? No. What did I do with that? Okay, so I'll go back to this image. So on top of that, you can see that there are 1, 2, 3, and I think you had 4 plates on there, maybe. And you can see the underside here. Okay, and let's go. Maybe I've got the close-up of that. No, I don't. I must have put that in a different directory. Okay, so you're seeing this view, but from the underside, and effectively he's got several layers. So in this section here, where you've got the two like crescent shapes, there is a bit missing from this view you can see here, and I believe that bit is missing because that is what we have on our microscope. This thing here, if I switch to that, this thing that you are looking at here is that missing piece from this view that you are seeing here. So this is that section, and if you looked at it from the other side, you would see that this is the backside of that piece before he put it into the reactor. So that is the bit that we are looking at, and then these pieces of brass were piled on top. And in fact, he's got some other views. So that is a larger view of it. And if you looked at a round anode, during an experiment, you would get something like this, and you can see these two layers of the brass and the plasma glow in between. And you can also see that it's not a continuous glow. There are actual subdivisions within that glow, and geometry really matters. So there is actually an actual gap between these two, and that might actually be very important, and it's something that can be studied. And so if you look at this shot, this is again part of these panels but a little bit closer up. You can actually see there are round sections here, these little round bits. Maybe I can zoom into that. Can I zoom in? Is it going to let me zoom in? How would I zoom in? If this was on a Mac, I'd be way ahead of this. I don't quite know if I can zoom into that view. Can I zoom in this way? No. Anyway, all of these images will be shared in the newsletter, so you'll be able to look at that. But you can see it's kind of got this like sawtooth gaps here. And if you can imagine, here, these are round areas here. You can see the balls on this and the balls here. These round areas are the plasmoids that, or the exotic vacuum objects, or these coherent matter structures that are appearing here. Now, if we look at the underside of this, we're going to see the exact mirror of what we are seeing on this. Okay? Now, look at this here. This was underneath the top layer. So this is the top layer, okay? And the gap that you are seeing here with these little round holes all the way down here, which you are seeing as the thing that was affected by the electrode, resulting in these balls here, and maybe this is a better image, these ones. This is what's causing those gaps. If we go to this one, you can imagine that this line that you see on the cathode here, with these individual balls, okay, they are what you are seeing here. And this is the center line, okay? And the channel is where there's a ball, okay? Okay, and what's happened, I believe, is that these coherent matter structures have got very, very powerful, and then they've splayed out here from the center line. And so if I actually take a different colored pen here, and what we've got actually is we've effectively got our piece of brass on top here and another piece of brass on top here, and the balls have created themselves in here on the cathode, and then they've got energized, and this magnetic fluid, this coherent matter, has come out and it's bored these channels. And because you've got two layers of brass, you can imagine that it would be cutting not only into this one, it would be cutting into the layer above. And also that anything that's coming out of this, I'm going to choose a different color here. Let's try some green. Let's say we've got this tendril here, and something comes out. It's much smaller quanta, and it's been released from this matter here because maybe it's become unstable. This potentially is what's causing these melt areas over here and over here, because you actually have these wildfire areas that are completely separate from the area around them. So it's like almost something jumped from here in between these two brass plates. Now you're going to see, Sakari mover, what the other plate looks like. And this is what the other plate looks like. And I'm going to switch to it now. So this is the two plates that were on top but the underside of them. And it's the exact mirror image of what you see on here. So there are actually three samples that came out of this experiment. You have the two from the top plate, which you can see if we look here. These are these two pieces. Okay, so you've got piece one, if I can draw on it. Let's see if I can draw on it. You've got piece one here and piece two here. I'm going to cancel that and we'll go to the other view. Here. So I guess that this is piece one and this is piece two. Okay, and piece three is the piece that I have been showing you yesterday and in the last couple of days, and that is the piece that was at the bottom. And so this is one contiguous piece. There is no break, but the break was here, and the plasmoids formed in the gap between those two parts of that brass and you can see that here. And so this is why you are getting this thing here. Now maybe I can play this. Is it going to play me? It's going to allow me to play, or is it not? No. This is when I'd like to be on a Mac. Okay, so basically it's burning these channels here. This is where the plasmoids are forming, and then they are bleeding out, and they are showing themselves here. So does that make sense to everyone? I mean, can you see what I'm saying? Are there any questions? You missed the start. Oh dear. Well, you can go back and look at it. Let me see. Okay, so, well, there's no, James, it's not likely to be copper sulfate, but it could be, because there is a very small amount of residual air in all of the Henk experiments, because he doesn't have the most amazing pump, and it's quite a large volume. It's 40 centimeter chamber, and it's obviously got length, and so, well, that particular one was, and so there will be some residual oxygen in there. And also, oxygen is one of these things that gets synthesized very, very regularly. Why do I say that? I say that because I think crustal abundance actually tells you what nature wants to produce a lot of. And if you look in the crustal abundance, what is the most abundant element in the crust? Oh, could it be oxygen? Okay, so, and then silicon, and then I think it's like aluminium. And so oxygen is quite likely something that could be synthesized, and one of the classic transmutations that you get when you have oxygen in a Lena reactor and you've got the active agents in there is 2 oxygen 16s become sulfur 32. So if you actually go and look at snowballs on cobblestones, this is in a structure that was formed on a 10 yen coin in Amasa gas testing in Japan in 2019. And what you can see is, you can see on the copper oxide layer there are these channels where these plasmoids, this coherent matter, these exotic vacuum objects, has gone around and it's captured the oxygen from the surface and it's transmuted that into sulfur. And so you can actually literally see these little balls moving around, and you can imagine them doing something similar here as it's moving around, as these are getting more energized. And you can see that they self-organize. Here, you have them self-organizing on the anode. And here, you see them self-organizing on the cathode. Here. So they're like, but they don't like enough each. If there's only a certain amount of structure to go around, they don't bleed into each other. If it gets too intense, they do bleed into each other. And we've shown this on many experiments. Okay, so here's, I think, a far view of these plates. So again, you can see from the top view here, this is plate 1 and this is plate 2. And then if we flip those over, cancel, and we flip those over, and we go into the further view. Again, this is plate 1, he says, plate 1 and plate 2. Okay, and this center section here that we see here is the exact mirror of what you are seeing on our sample here. If I move the microscope out of the way, you'll get a better view of it. There we go. Okay, so anything there? Would be cool to do a Zoom live stream. Yes, I might consider that, yeah. Actually, like boron is not terrestrial element. Okay. What material is that anode? I do have a note on that when I add more detail into the blog. I will tell you what it is, but it's definitely not iron. It might itself be brass, actually. Looking at the underside of it, it's got a kind of a brassy look to it. If you look at that, so it might actually be brass itself. It's definitely not magnetic. We demonstrated that earlier. What's the reason for the arrangement of the pieces of metal? I think I said this earlier. Basically, the port that he can take the bolts off and put stuff in is not big enough to put one large cathode electrode in, and of course the bottom of his reactor is curved. So if we go back to that drawing that I showed earlier, so here, so his it's a cylindrical pill shape. It's cylindrical in the center section, and so he wanted to get a flat cathode in the center, so that he could produce a fairly flat field emission towards the anode, and there's 10 centimeters between the cathode here and the anode, and so you've got a curved structure here, and that's not what he was going for, because he was going for something that may be a little bit like sapphire. So by having this flat structure here, that's similar to what sapphire are doing, I guess. And so he built this thing that he could put through the hole and then assemble in the chamber by going through the hole. So I've got some other notes here that maybe I can go through that might be relevant. Yeah, so I think the key takeaway from this is that this is quite repeatable, you would imagine, because it's effectively an effect that happened between a gap. So we have, if you look at this image with this anode here, you have this gap between two plates here, and you have this concentration of the glowy stuff in the middle here, and they are also bulbous along the gap there. And from this view, from this view here, you can see how these come about. And basically you can imagine that you could produce this kind of every day of the week. And if it does actually do transmutation, then you have a reliable way to make some extremely interesting pieces. And I would suggest, actually, that it might be nice to fashion, rather than a straight line, and maybe I can just draw on the top of this frame here. Maybe I'll go to this image because I'll get more clean area. Rather than having just a straight line, what you could do is you could have your anode here, and actually I like the idea of the kind of chamfered billet anode. So you have your chamfered billet anode, and then actually your cathode would actually be a disc, and then a disc with a hole cut in it, so that you actually have a circular groove. If you can imagine. So you've effectively cut out a little button in here, and then there's this gap here, which is the equivalent of the gap that you're seeing here. So rather than a linear gap, you have a round gap. And that's really bad what's done there. So you have a round gap, and you have material here, which is your brass, and then you have another piece of brass in the center. So you effectively create an O, but it's the actual gap where you want to see the action in there. So I would imagine that if you did this, if I can do one step back, we would see our little like organization of plasmoids here, and then we would get, it would be interesting because we would see how these radially fan out, and do they then branch like this until they get close to each other. This is kind of the experiment that I'd probably like to see being done, and it's relatively easy to do, obviously when you've got a reactor working as well as Henk has. So it'd be interesting to see what happens there, and I'm open, and Henk is, to any and all ideas about how to proceed this. In fact, you could start with producing a whole bunch of concentric rings like this, and by rings I mean the gap is the hole. So you're creating a load of discs with a gap, so multiple gaps. And it would be interesting to see how that progresses. We already have very good data, because we know in the kind of setup that he has, when the anode is 10 centimeters away from these two sheets, that the span of the effect, it only goes out to a certain level, okay, and then the secondary span, it goes out to a secondary level. So you would actually choose a radius that was kind of like that kind of radius, and we know exactly what that is. In fact, I can tell you what that is right now by using this. There we go. If I can put it around the other way, maybe get it in shot. Is it going to work roughly? So it's going out. Wrong angle there. Is it going to? It's too much light. I'm going to kill the microscope. Sorry. Okay, so you can see the 30 millimeters, maybe maximally 32 millimeters there. So you could design your button in a hole plate and work on that basis. Okay. So what do the underside of it? Okay, so we've done that. Wow, does it boom? So yeah, you could say that some of the brass would melted down, and it's interesting. It is very clear. Let's go to some of our images that we shared yesterday here. So this one here is rather nice if I flick to it. And again, it would be nice if it actually played GIFs. Okay, I'm going to have to find a better viewer. So your deep channel is over here, and this is kind of a secondary spillover channel. So you can imagine what happened was when this was charging the channel up here, and these balls got quite intensive, these coherent matter started to splay out underneath in between the gap, and that would then reach here. But when it got really, really intense, it then breached this boundary and came over here. But the interesting thing is that whilst this is flat, it doesn't look like it's bonded to the upper layer, and so it's kind of like it was churning the material from the bottom as well as churning the material from the top in equal measure. But the coherent matter may actually be covering the material that's being churned out, and it kind of repels. So there may always have been a gap between the upper sheath and the lower sheath, where if you can imagine that the ball of fire's there, and as it's eating this material, maybe it's coating it with something, and as the two bits get closer together, they actually can't actually meet. And I'll just have to check with Henk, but it certainly does not look like, when you are looking at these things, that you've snapped it off the top level. So it just looks like it is. Maybe I can go here. It just looks like it wasn't attached to something above. It's nice and smooth and bulbous here. And by the way, this is very, very similar to the structure on the Hutchison sample, where you have these radial features around it, and this raised edge on it. Except in the case of Hutchison, his was done cold. It was not done with this ostensibly many hundreds of degrees, and so his coherent matter was able to do the same thing but without being at more than room temperature. Okay, so yeah, it's definitely not connected, as it were. It's flat, and unless it just grew and grew and grew, and no, I can't imagine it. If this was molten, I would have imagined that the top layer and the bottom layer would have fused together, but they seem to have been able to be separated really rather easily to give you this, which is a mirror image of what you're seeing on the bottom. So I'll have to check with Henk to see if he had to really go to a lot of effort to crack these apart. But when you look at the images that we have here, they really do look like they are just smooth on this top side here. Okay. Do you have those two slabs or only the bottom one? Unfortunately, I only have the bottom one. Yes, Gordon Doherty. Whatever caused those tracks, which I believe are effectively that you're building your coherent matter here, and this is your charge zone, but it's getting trapped, and so from let me draw that there in between the two plates. So this is the top of a plate here. That's the top of a plate, and the top of the plate's over there. So you're looking at this with a perspective like that, okay? And so what I'm suggesting is that in between the two plates, of which this is the gap between the two brass plates. I'm suggesting that underneath there, this coherent matter is spreading out. And it might even be branching out because it can. It's got somewhere to move. And so it's one thing to have balls on the anode, okay? But actually I think this is much more fascinating. And it has the potential, you know, to remediate nuclear waste. I mean, this isn't, in my view, the most optimal way to do it, but you could, between the two plates, load it up with an isotope you wanted to get shot of, you know, and if you know the radius to which it is going to, or the level or distance to which it's going to move, so you could literally in this zone here and this zone here, you could put basically several millimeters of cesium-137, right? And these little plasma borers are gonna, or these coherent matter borers are gonna come out, and you know, eat this stuff, and maybe convert it into carbon or something. So I mean, these things will be an easier thing to discuss when we've looked at it under the SEM and found out whether there is actually transmutation going on. I believe they are self-organizing because of magnetic fields, and I discussed this on the blog, and you can go to it at remoteview.icu, and I shared a paper from, I think it was 1983, where magnetic fluids self-organize, and I believe that's exactly what you are seeing in these images here. You are seeing magnetic fluids self-organizing. Maybe I can bring that up, and just cancel that. I'll just go and bring that up, shall I? Where's that? Just bear with me a second. So on the magnetic fluid subject, can actually show you these things now. Maybe I can go here. Okay, so I showed this thing yesterday, and here it is again. And so on the left hand side here, if it's going to work, is it going to work? Why is it not working? Oh wait, I don't know why that's not working. Okay, on the left hand side here you can see magnetic fluid up here, and these channels in my view are essentially exactly the same as these channels that you see here. A dielectric fluid behaves quite differently, and so depending on the field between those two, you would get a different dimension structure, and depending on the gap. So high field, small gap, you get small features. High field, large gap, you get this low field, large gap. So what we are suggesting is we are having in this a low field, large gap, which kind of makes sense because they're not so far apart, are they? And you know, kind of makes sense, really. I mean, actually, they're self-organizing for the same reason that kind of these things are self-organizing. You know, which you're seeing here. These self-organize, and if you go and look at remoteview.icu, you will see lots of examples of these things self-organizing. So back on this one, I just show you a couple of other things because these are some images that I put out, and they're actually a much higher resolution. You can download the full resolution ones here, and I will put up more stuff from today. Now what I did on this one is I took a near field and a far field, and I merged them together on 2 frames, and then I stitched 2 frames together. So this is actually made of 4 images, and we would like to get a optical spectrometer, and I've identified one which I can get from California for about $750, $800 shipped to Europe, and I would like to run that with the supernova reactor to see any real-time potential transmutations, and also then to ship this and work with Henk on seeing if we can observe real-time transmutations. And you know, I don't want to ask for something without giving something, and I just wondered if there's an interest in the community for me to spend quite a considerable amount of time to effectively do what I've done here with 4 images, but to do it for the entire structure and produce a very nice poster. And I just ask, would people be interested in a really nice big poster of this very high definition, and would they be willing to help contribute to getting that spectrometer so we could see if we're seeing real-time transmutations in both the supernova reactor and the VEGA reactor. So if people are interested in that, let me know, and I might put up a funding request for that if people think they can help with that. Okay. Okay, all right. So I actually haven't done what I wanted to do initially today, which was to have a closer look at many of the features in these areas and do some scaling on it. So maybe I can have another session tomorrow or at some point over the weekend and to have a look at those, because I think that people want to, or I want to at least do some dimensioning on those, and I think that would be useful. But it's again gone past my curfew time. So what I will do is I will add to the description I have on the blog, and I will add in these various images and so on, and just tell the story of how the anode was constructed. But I think the major takeaway really from today is that it's not a story that's just about the anode. It is really a story about the cathode, and almost we can do more interesting things with the cathode than we can do with the anode, and the potential for producing transmutation here. If this genuinely has got transmutations in there, and I actually suspect it will do, bearing in mind one proviso is that if our anode here is made of material and you get ions produced of that material, that these are positive and they will drift to the anode. So what we are looking for are elements in the gap and in these channels here that were neither brass, i.e. lead, potentially tin, copper, zinc, and not the elements that you would find in there. So we're going to be looking for some interesting elements that were not in the reactor to begin with. But that being said, if you looked at the presentation that I gave here yesterday, or rather the actual blog, if I can find it here, and you run the reactions in the MFMP fillet power reaction calculator here, you end up with 6,241 reactions returned, and it produces 275 nuclides. So there's and all stable, and so, or pretty much, and so there is a real potential to produce vast numbers of elements that aren't already in the materials that are there. One thing that I will say as a proviso: if there's a more energetically favorable reaction, it will tend to do that first, and also if it gets to push it too far, it'll just generally strip things down into alpha nuclei, and then it dumps out a load of carbon. And so that's maybe what a lot of this is here, and that's something that's been observed by Matsumoto and Yul Brown and us and so forth. So anyway, okay, so I think I've nearly had enough. So what I'll do is I'll look at your comments at my home, and so I think I'll say thank you very much for your time, and it's a real pleasure to have the opportunity to look at these things. Again, I want to thank the people that have helped put this kit together effectively, and you know, we have a lot of samples to look at, not just with the VEGA experiments, but also with AMASA experiments. I have some separate samples that came in a package some time ago, which were done from experiments where I wasn't present from AMASA. And so we have a lot to work through, and if you think these sessions are useful, then I might see fit to do more of them. Anyway, so thank you. That was the what do we call it? We called it Valley Forge, and this was a presentation to explain how this particular VEGA reactor produced these tracks. And again, if you have any questions, go to the newsletter on remoteview.icu and we can deal with them there. So thank you very much for your time, and I'll see you soon.